Today we're diving into the fascinating world of physics to explore the Magnus effect. Ever wondered why a spinning soccer ball curves in mid-air? Let's find out! The Magnus effect describes the phenomenon where a rotating object moving through a fluid experiences a force perpendicular to both its direction of movement and its axis of rotation. This force is called the Magnus force, also known as the lift force. It is named after the German physicist and chemist H.G. Magnus, who first experimentally investigated the effect in 1853. The Magnus effect is a key concept in fluid mechanics. Some applications include fluid flow and rotation. When a rotating object moves through a fluid, like air or water, it alters the flow of the fluid around it. This interaction is a fundamental aspect of fluid mechanics. Secondly, pressure differences. The rotation of the object creates differences in fluid velocity on opposite sides of the object. According to Bernoulli's principle, these velocity differences lead to pressure differences, which result in a force perpendicular to the direction of motion, which is the Magnus force. Thirdly, boundary layer dynamics. The rotation affects the boundary layer of fluid around the object, changing the flow characteristics. This can lead to other phenomena such as lift in aerodynamics. Lastly, applications in engineering and sports. Understanding the Magnus effect is crucial for designing objects that move through fluids, such as aircraft wings, rotor ships, and sports balls. Engineers and scientists use principles of fluid mechanics to predict and optimize these effects. Understanding how rotating objects interact with fluids allows for innovations in technology and sport, thus performing in its fullest potential. To explain the Magnus effect, a lateral force generated in a rotating object can be attributed to the rotational motion of the surrounding fluid driven by the rotating object. Imagine a soccer ball spinning as it flies through the air. The rotation of the ball affects the airflow around it. On one side, the ball's surface moves in the same direction as the airflow, speeding it up. On the opposite side, the surface moves against the airflow, slowing it down. According to Bernoulli's principle, faster moving air creates lower pressure, while slower moving air creates higher pressure. This pressure difference generates a lift force perpendicular to the direction of motion, causing the ball to curve. This is the Magnus effect in action. This force arises from the Bernoulli equation for streamlined, non-turbulent flow, where kinetic energy density plus pressure equals a constant. The gravity term ρgh is negligible and hence omitted. Next, let's consider two cases. In the first case, when a vortex is moving through a medium at a speed v, from the viewpoint of an observer in the vortex, the medium will be moving at a speed -v instead. In the second case, on one side of the vortex, the velocity v of the circulating current adds to the velocity of the medium, while on the other side it subtracts from it. For these two cases, we will assume that the kinetic energy density plus pressure equal constant in scalar form. Since the kinetic energy is greater for the positive sign, from the above equation it follows that positive pressure is less than negative pressure. This pressure difference causes a force F lift to be exerted on the moving vortex in a direction at right angles to its velocity, towards the lower pressure side. However, it is important to note that in real-life situations, non-ideal flow may be involved where boundary layer separation can significantly influence the Magnus effect. Boundary separation layer occurs when the smooth flow of fluid around an object breaks away from the surface. This separation typically occurs earlier in non-ideal conditions due to factors like surface roughness or adverse pressure gradients. Thus, for real-life situations, it appears later as flow remains attached to the surface for a longer distance. This delayed separation can enhance the Magnus effect by maintaining a higher pressure difference between the two sides of the spinning object. As a result, the object experiences a stronger lift force, leading to a more pronounced curved path. To end off, here are a few other external effects that may come into play. Firstly, buoyant force. Drag force acting backwards may slow down a ball. Secondly, for balls with seams, there is a side force acting on the ball. Most importantly, do not assume that air resistance is negligible. Before we end, here is a simple experiment demonstrating the Magnus effect.
Today, we will explore the Magnus effect through a simple experiment with a ping pong ball and a rolled up piece of paper. First, we roll a ping pong ball off the table, then we did the same with a rolled up piece of paper.
When the ping pong ball rolled off the table, it continued to roll forward as expected. However, when the rolled up paper rolled off the table, we observed that it rolled backwards, opposite to its initial direction. And this phenomenon is explained by the Magnus effect.
So next time you see a curving soccer ball or a spinning tennis shot, you will know that it's all thanks to the Magnus effect. Thanks for watching!